I am Jonas Seng from the AI/ML group at TU Darmstadt, and I'm going to present a joint work with Fabrizio, Ventola, Zhongjie, and Kristian Kersting titled Hyperparameter Optimization via Interacting with Probabilistic Circuits. Hyperparameter optimization is a well-known task where we have given a black box function f and a search space x, and the aim is to minimize that black box function. However, we do not have any information about f, so we cannot use, for instance, gradient-based optimization methods. However, we can query f in order to evaluate configurations. A well-known strategy to optimize such functions is Bayesian optimization, which recently got augmented with user priors, meaning that users can guide the optimization process in order to find better solutions or good solutions faster. The idea is to optimize the black box function as usual. So we start with querying f at random points, fit a surrogate s in order to capture the dependency between the search space x and the evaluation space. Then the next configuration that is deemed to be most promising is selected using a selection policy that leverages the surrogate s and a user prior q. Then the selected x prime is queried, or f is queried at x prime, yielding a new evaluation score, and the surrogate model is updated. And this is repeated until convergence. However, we found that existing state-of-the-art BO methods incorporating user knowledge do not reflect the user priors well. On the right-hand side, there's an example for the JAS benchmark where PyBo and BoPro do not reflect the given user prior here in purple as they should. In order to improve upon that, we propose to use probabilistic circuits as surrogate models. Probabilistic circuits compactly represent a joint distribution over a set of mixed random variables that can answer to a broad set of probabilistic queries, such as marginalization and conditioning, and that also can conditionally generate new samples. These models consist of three types of nodes: sum nodes, product nodes, and leaf nodes, and can be interpreted as a hierarchical mixture model, where the sum nodes represent mixture distributions and the product nodes represent product distributions. Based on PCs, we derive an interactive sampling policy that is flexible and tractable thanks to the efficient computation of conditionals of PCs. And we could easily integrate a recovery mechanism to be resilient to harmful feedback. This is something we have done in further work. Regarding results, we find that our proposed method IBO-HPC, finds good configurations quite fast. So in the case if no user feedback is provided, the blue line, we find that IBO-HPC finds state-of-the-art results. And if beneficial user feedback is provided, so the green and orange lines, we see that our algorithm improves in terms of performance and in terms of speed. And also if multiple interactions and possibly even harmful interactions are provided, our method still manages to recover from that and uses multiple interactions. In terms of speedups, if we have given beneficial feedback, then we see that IBO-HPC is capable of accelerating the optimization up to 12 times. And to conclude, we proposed a fast and efficient Bayesian optimization method that allows for incorporation of user feedback in a flexible way. And we have shown that we outperform state-of-the-art in several cases.